Hi. In previous video, I talked about TensorFlow. I gave a brief overview of TensorFlow. In case if you have not watched the video, you can click on the link in the top and watch it. But to give a gist, we saw various ways of accelerating TensorFlow. It can be on a CPU device and GPU device. We saw how a mathematical computational formula can be broken down and run on multiple device accelerators. And then we also talked about various features of TensorFlow. And then finally we saw distribution strategy. In this video, this is a two-part video. In this video, we are going to more focus on GPU based acceleration. In the next part, we will be talking about TPU based acceleration. Coming to this part, in this part, we are going to walk through an end-to-end model development in TensorFlow on GPU. It can be run on CPU as well. We are going to see how with a change in a small syntax, how we can run it on CPU. We are going to take a data set. We are going to take a image data set. We are going to run a convolution neural network or using Keras. We are going to evaluate various metrics. We are going to try to increase the accuracy. We are going to see Tensorboard. And then finally, we are going to train the model, take the trained model and then deploy it again, run it in Keras and inference it. So this is going to be the structure of this particular video. So let's get started. Now, I am as usual, I am using Colab. Now, in order for us to run in GPU, just make sure you go to runtime and then change runtime type. You make sure you are selected GPU. There is none. That means you get CPU, GPU, and then TPU. In the next session, we will see TPU, but make sure you are selected GPU over here. And once you are selected the notebook, just to make sure that that you have GPU and a proper GPU is allocated to you, you can run the NVIDIA SMI command. Basically, it shows the type of GPU that is allocated to you and also what is the current usage. So basically, we have got a Tesla T4 GPU and then the usage currently is almost 0. So you can just verify it, and in case when you are running it, when a process is running this command, you are running it when a process is running, you can see the process over here, what process is running and what is the GPU memory used by that particular process. So now we have our GPU ready. So first thing what we will do is we will import our packages for TensorFlow. So in Colab, I'm just making sure Colab has like 2.x version. You can also pip install it, but I'm just going to use the Colab provided version. So I'm just making sure that I am setting it to 2.x. If the 2.x is not there, then I'm just throwing an exception and then I'm importing a regular TensorFlow package, right? And then what I'm doing is I'm importing other packages. I'm importing TensorFlow dataset. So for this particular demo, we will be using a dataset from the TensorFlow dataset repository. Basically, TensorFlow dataset provides a list of datasets that can be directly used in TensorFlow. You don't have to explicitly download it. Basically, when you use this TensorFlow dataset, it will download that particular dataset. And then also I'm loading the extension for Tensorboard. This is to visualize the output of the model. So let me run this and then yeah. So basically the TensorFlow 2.x is loaded. What I'm going to do is just to show you, don't use that in real production, it will do too much of login, but just to show you like what device is used in what purpose. We'll be doing some tuning where we'll control what data we want on GPU and what we want on CPU. But if you set this, it will give all the debug on the information on where GPU used and CPU is used. But in case of production or real world, just disable it. Don't set it at all. By default, it's disabled. So now I'm going to enable it. You will see a lot of logging, but it gives us idea on what is getting used. And then I'm going to see the devices that are there. So this will list all the devices that are there in this particular server. If you see, there is a GPU which is indexed by 0 and there's a CPU which is indexed by 0. If you have multiple GPUs, then you can see GPU:1, GPU:2, GPU:3. XLA is nothing but compiler which speeds up your computational graph that TensorFlow generates. So you have one CPU and you have one GPU over here in this case. Now this is the command I was talking about. So what I'm doing is I'm importing TensorFlow datasets and then I am downloading the fashion dataset, which has basically all the various like categories like dress, sandals, and there are 10 categories over there. Basically, I'm downloading that data set and we'll use that data set to develop our model. And I'm just doing a TFS load over here. I'm just asking the info. This will give info on what the data, what that particular data set has, how many rows, train or test data set. I'll show you that. And I'm telling it's as supervised. Some of the data set are available as both supervised and unsupervised. So I'm just making sure I get the labels as well. And try GCS equal to true must be set for TPU based inference. But here I don't need it, but I set it, that's fine. And I'm telling get me both train and test split. Alright, so that's what I'm doing over here. Let me run this. It will take a few minutes. If it's already downloaded, it's going to just go and take that particular data set. But since mine is already there, you are not seeing any output. But when you're running for the first time, it's going to download it into your local environment, and you can see basically the data set downloading. And what it is telling is all this particular data set, what fetching the data set and slicing the data set, prefetch data set, everything is running on a CPU. Because typically fetching a data set or SFTPing a data set does not require GPU. So these are all CPU operations. As I said, you will get a lot of output. But if you have disabled that one, you will not get any output over here. But for now, just for the demo, because I want to show you how I can control the distribution strategy on what needs to go on GPU and what needs to go on CPU. Now the info is, we are given info true, so we'll get all the info about this data set. If you see over here, basically the fashion means data set. I have like total 70,000 examples, 60,000 is train and 10,000 is basically test, and I have both image and label over here. It's just providing information. I can just pass specific information from that info. So I'm seeing basically the future dictionary, the image shape is 28 by 28 by 1. So it has only one channel and it's 28 by 28, and the class labels are, there are 10 classes. And these are the 10 classes. Basically, the output labels are whether that particular whatever dress or fashion equipment, fashion that we wear, right? So basically, it's basically a t-shirt or trouser or pullover or dress. It has 10 category. So what retail segment? What is the output? Now, what I'm doing first thing is I'm taking that particular data set, right? The data set is my object that I have created over here. And I have train and test. So what I'm going to do is I'm assigning that to basically fashion means train and fashion means test variable. Dataset 0 is train and dataset of 1 is test. And further what I am doing is from the test data frame, I am taking 3000 rows, 3000 images, and I am assigning it to validation data set. So basically it has 10,000, test data set has 10,000 images. Out of that 3000 I am taking in assigning it to validation, and I am skipping the 3000. So basically it's going to take in order. I am going to skip the 3000. So remaining 7000 that is left will go into the test data set. So that's what I am doing here. So I am creating train, test and validation for our model. And this is also a CPU activity. If you see the train, it will tell it's basically an dataset object. So now TensorFlow also has a tf.data where you can go and import a delimited file or fixed width file, or even you can take a tf record. Tf record is kind of the base format for TensorFlow. If you want to distribute and run it, tf record is the format to go. But you have various way of loading the data. You can read the tf.data documentation. Now what I'm going to do is, there is no function like pandas over here where you can go and count the number of rows. So what I'm doing here is I'm just listing the number of rows over here. The FM train I'm passing to a list and then calculating the length. So it's going to take some time. It's going to go and count the number of objects there in the train basically frame over here, the training frame, and it's 60,000. Again, this is a CPU operation, right? Now I'm just quickly going to view some of the labels, some of the images, and see the labels. So I'm just using the typical matplotlib, and basically what I'm doing is I am taking my training data set, I'm taking 5 rows and I'm iterating it. I'm taking the image and label, I'm just doing an basically numpy plot image show, and you can see basically this is what the image of ankle boot is, and similarly like you have headdress image and whatever next, just a minute. Yeah, you have a sneaker, you have multiple categories. I'm just showing some 5 images for us to quickly visualize a shirt, and then yeah, that's it. So these are the 5 images. And then what I'm going to do is I'm going to, for my Tensorboard, I need to log all my model metrics. So whatever my model is going to generate, I'm going to use callback function, and I need to log my output so that my Tensorboard can visualize it. So here I'm going to just create a directory in the temp /log. So it will create a directory. So it's already there because I think this session I already ran it last time. So that directory is already there and we are going to use that. Now the next thing is I'm going to basically scale the image. So my image is going to be between like 0 to 255. I want it between 0 to 1 so that my algorithm can work faster. So I'm just going to scale the image. You can run it as it is as well. But just that my output is between 0 to 1, so that my gradient descent algorithm can converge faster. I'm going to just scale the image, and there's a function I have created. So I will call the function in all the data set, but this is to scale the image. And next is what I'm doing is I am creating the scale using the scaled function. I am scaling the particular train, test and validation data set, and also in the train data set I am shuffling the data set and taking some batch of records. So basically we are going to use a mini batch gradient descent, and I'm passing data set in batches over there. Now I kept 64 over here, but you can increase it because you are using GPU. You need to check like how much memory you have, and what is basically, if you're on CPU you want to keep it low because you cannot parse a lot of data set at one time. You maybe want to keep it to 8 or 16 or 32, but in GPUs you can even go to 200. In this case I'm just kept 64 so that I can use this to run my CPU based inference as well. I'm scaling, I'm shuffling it, I'm having the batch size, and then similarly I'm doing for test data set and validation data set. I don't have to shuffle my test and validation data set, as I'm just going to, it's not going to be seen during the training time. Even though validation is going to inference, it is not going to be used for training, right? So I'm having this data set. Now I'm going to create a Keras model. So this is an image data set. So I have a convolutional layer. I'm going to keep the model as simple as possible. The idea is not to get an best accurate model, but to more see the functionality of TensorFlow and how we can use various distribution strategy to control the execution of that particular model. So here I have an Keras model. I have a convolutional layer which has 32 filters and kernel size of 3. If you need more information about convolutional neural network or any neural network, maybe I have attached a link in the description of the video. You can go and refer it. If you already know, basically a convolutional neural network works better on images because it is not like translation invariant and scale invariant like your typical feed-forward neural network where you convert everything into an array, right? Now you have a max pooling layer. This is to reduce or downsize your sample size as we move, reduce or sample size your dimensions as we move into the next layer. And then we are flattening out the entire output from these two layers. And then we are creating a dense layer with 512 neurons. Activation is value. There are multiple activation functions again available. We are dropping out the final 20% in the layer, and then we are using a dense layer which is nothing but number of classes, and we are using a softmax activation function over here. This is the number of classes we have in our data set, right? Now let me run this. So we have our model created. Now everything what I have done is I have created a function. There's a get dataset function to get the dataset. There's a create model function to create the model. Now what I'm doing is I'm coming to the training of my model. I am assigning model to the create model, which is our Keras model function on top. I compile the model. I'm telling my optimizer is Adam optimizer. My loss function is basically sparse categorical cross entropy, and my metrics is accuracy over here, right? And the log directory, this is the directory that is used by Tensorboard. And if you see, I had created on the top, and I'm telling my log directory is basically temp/logs. And then I'm appending a timestamp to that particular log, so that if I'm running multiple versions of this model, everything will have a separate log file over there. I am also calling like Tensorboard callback function and passing a log directory. So in Keras, what I can do is I can give callback functions to execute as the model is getting trained to record the training steps or training output, right? So that's what I'm doing over here. And then I'm getting my dataset function. I'm using a get dataset function that defined on top, which creates a train, test, and validation dataset. Because if you see on the get dataset function, I am returning the scaled version of the 3 datasets. So you will get all the 3 dataset over here. And then I am I'm creating a cache of my train and validation dataset before feeding it in the model. Then I am kind of doing a model.fit, which will start training the model. I'm just running it for 5 epochs and I'm giving like 20 steps per epoch. We will see where it runs as we go into the detail of it. And then I'm giving a validation dataset so that I can see like in every epoch, what is the validation accuracy, just to make sure that my model is not overfitting. Right, and then the Tensorboard callback I'm giving over here so that I can visualize the output. All the information is recorded in Tensorboard using this Tensorboard callback in this log directory so that I can visualize that in my Tensorboard. And I am also printing what is the distribution strategy used by default. If you see, as of now, I have not given any distribution strategy. So I'm going to see what is the default distribution strategy. So let me start running it. It may take hardly less than a minute. So now if you see the output over here, you can see a lot of these operations that TensorFlow creates internally to create the computational graph. Everything is running on GPU over here by default. There are some CPU as well. Now the model is trained, and if you see the last epoch, basically you have a model with 75% accuracy. And also the validation accuracy is close, 76%. So model is not overfitting. It's not like great because my model complexity is not there. I just created one convolution layer. We can try to increase the epoch and see we can try to increase the convolution model complexity and see there are multiple things we can do. And what we are seeing here is using a default distribution strategy, whatever Tensor default distribution strategy is. Let me talk about the default distribution strategy. Now, if you have a GPU device, and you have TensorFlow GPU installed, it's going to run it on a GPU. But the data, if you really see this step, right, it's on each epoch, it is basically picking the model data set from CPU, not GPU. So in this case, the data is sitting in a CPU system, and only the execution of the computational graph that TensorFlow creates for this particular Keras model is running on a GPU. So on every epoch, there is a data set movement between your CPU to GPU. So this is the default distribution strategy over here. And let's go to Tensorboard. And then in the Tensorboard, if you see, I'm just using this magic function. And then I am using this logging directory where I created the logs. Let me enter it because I had a previous run also. Maybe you may see multiple logs, but let me filter it out. Let me just give some time. It will take some time to load. Yeah. So you're seeing a lot of output because these are all from previous run. I'm going to just remove all of this, what was from previous run. Yeah. So now if you really see, we have run for around like 5 epochs, and finally this is the loss, epoch loss, and the loss is also reducing as you see the graph. Basically the loss is coming down, and bottom one is basically you have the accuracy. If you see, the accuracy is around 74 and 75. The validation accuracy is 75, and the accuracy is also getting better as we train for more epoch. Now one thing that we can do is we can also go on the top and we can click on graphs. This will give you information on what was the computational graph that was created for our model. If you see, like we had a model where we have a convolutional layer, then we have a max pooling, then we flatten it out and we use the dense function. So basically it's creating this computational graph, and this computational graph is pretty optimized, and you can if you have multiple GPUs, you can even run it on multiple GPUs. There are multiple distribution strategy that helps us do it automatically. I will cover some of it, but other things you can read it on the website as well. So this is the computational graph it's create. One more thing like over here is the Tensorboard is not completely enabled for your collab environment. If you have a Tensorboard outside, you may get even more metrics. They are just working on it, but Profile is a very good place where you can go and see what was executed on CPU and what was executed on GPU. But in this case, they are not enabled all functionality, and you can see only CPU over here. So if you see over here, you are just seeing the CPU over here. So, if you take this, if you download the output from the log directory and then use your Tensorboard and upload it, you can see even better visualization. And it tells like each and every iteration, what was used, how much time it takes. It has a lot of information. So this is like Tensorboard. I will go to next step and again come back to Tensorboard. Now what I'm going to do is I'm also going to check whether how much of my GPU is used. So the NVIDIA SMI command will show you the GPU utilization. Now if you see here, earlier it was 0, now almost like 745 MIB is used, right, megabits is used. Now what I'm going to do is I'm going to increase the complexity of the model, right. Now also I'm going to set a distribution strategy. There are multiple things I'm going to do and see like how the model behaves. In this case, apart from a 32 convolution filter layer, I'm adding one more convolution layer with 64, and the remaining is almost same, right. So I'm just added one more layer over here, and I am setting a distribution strategy as mirror strategy. Earlier you saw it was a default strategy. Here I'm setting a mirror strategy. So what mirror strategy does is, it works on a single node, and in single node, if you have multiple GPUs, it makes use of multiple GPUs. So rather than having the data on the CPU, the mirror strategy creates a copy of the data on the GPU. And you can see when I'm running it. And if you have multiple GPUs, so basically if I have batch size of 200, right, it will kind of run like 100 batch size on each GPUs. So if you have 5 GPUs, you can even have a 500 batch size, right? You can basically manage you can run model very fast. You can configure a higher batch size, and even the computation will be distributed because it's going to act on chunk of data, and then it's going to sync up the final model variables. It uses an all reduce algorithm, so it takes care of syncing of the model variables across the multiple GPUs, and it's a synchronous method. There's one more method, asynchronous, which is parameter server strategy, that I'm not going to discuss here, but you can read on it. Now I set the distribution strategy, and I'm defining the strategy scope, and anything I define within the strategy scope, this is going to run it on a mirrored strategy. But outside of the scope, it is not going to use mirrored strategy. I'm again creating the model. I'm doing the same method. I'm creating a log directory. I'm creating a checkpoint. Basically what I'm doing is I'm going to get the final best model, right? So I'm creating a checkpointer over here. This is also a callback function. And then I'm telling that save only the best model. Here you can also tell it to save all the models, but I want only the best model over here, whichever give me a better accuracy metric, right? I'm going to use this model to load it back and do inference later, but that's why I'm creating checkpoint. I also have a CSV logger callback, just to store the output of this particular model in a CSV file. So if I want to analyze it outside, I can do it, but that option is available. The other things are pretty same. I'm calling the get dataset method. I have all the dataset. I assign it to history variable so that I can create my own graph. I'll show that to you. And then I am giving all the callback function. I have a Tensorboard callback. I have a checkpointer so that I can have the final my model saved. And then I have the CSV logger. And finally, what I'm doing is I'm saving that final model, whatever I get. And then I'm also printing the distribution strategy so that I can show you what was used. So let me run this, and I have increased the epoch from 5 to 10 over here. Now I have increased the complexity. Now if you see, everything is using GPU. There are few CPUs because not everything requires a GPU. When your model is done and you just want to finally take the output, you just need or save the model. What you need is nothing but a CPU. But in this case, let's see how the data behavior is. Now it's going to run for 10 epoch. It has run. And finally, if you really see because I added one more layer, the accuracy is better, and the validation is accuracy 73. So basically 78 and 73, you have some overfitting over there. Maybe we need to kind of add more dropout, or we need to see how to tune that, right? But for now, let's kind of concentrate on the TensorFlow functionality. Now one thing if you really see here, rather than the model data set that was getting operated on CPU, here it's using a prefetch data set operations which is on a GPU device, not on a CPU device. So by setting the distribution strategy as mirrored strategy, I just made sure my data is loaded over there, so that if I am training for longer duration, I don't want to move between CPU and GPU. I can directly use GPU. That is one more distribution strategy which is very similar. It's called multi-worker. So TensorFlow can scale from one node to thousands of nodes. So if you have multiple nodes and each node has multiple GPU, you want to use multi-worker mirror strategy. That is the other option that is available. But I have only one GPU over here. So, and I have only one node, so I am going to use this. And finally, let's see like our model is created. So you can see the model was created, and then the history is the output I am passing. You can print the history and it will capture everything on each epoch, what was it, right? So if you really see the loss it is capturing, how the loss reduced, it has the accuracy, or whether the accuracy was increasing or not. Now this information is available. What I can do quickly, I can generate a plot outside as well. I don't need a Tensorboard, but I can quickly generate a plot and see using that history function. Right now I'm going to go back to the Tensorboard. Since my Tensorboard is already started, what I can do is from Tensorboard I can import a notebook and then I can do a notebook list. So it will tell me the Tensorboard running instance. Right, so 6006 it's already running. So what I'm doing is I'm just doing a display over here that with the port number, and I'm just giving some height so that how I want it to be oriented on this notebook. Right, so now this is done. So it's going to load the Tensorboard. It's going to take few seconds. So basically, now you can do better control with multiple GPUs. That's what we saw. And when you're writing a custom function, that's what we are going to see in the TPU world, TPU demo. That in the next, we are not going to go with any model or something like that. We are going to take a custom formula and then execute it on a TPU. You can better control like how do you want to place that particular function so that you can accelerate. Again, I'm going to remove all my old one. I'm going to keep my last two runs that I did during this particular demo session. So I have only these two, and you can basically see how the output is. Right, so basically this is the previous run, and the orange one is over here. This is the, let me go a little. You can see basically the loss is this 10 epoch, right? So I agree, I'm sorry, this one, the blue one. So now it has gone till 9 epoch, and you can see how your validation accuracy is changing, right? In the fourth one, there was a 71 train and 74 accuracy and 75 train and validation. So basically that was very closer. The model was not overfitting, but when we went into the detail, the accuracy went to, so the validation accuracy went to 76, and there was a disconnect between the validation accuracy and the training accuracy. So that can be a cause of overfitting. So you can, based on that, if you are using a callbacks function to save multiple models, you can pick that particular model from a particular epoch and also use it. Alright, so this is like Tensorboard. Now if I don't want to use GPU, I have a GPU, I want to run it on a CPU, or I want to run it on particular CPU, I have multiple CPUs. What I can do is I can just go and create a device strategy over here. It's not a strategy, it's just a device function over here. And then I'm telling run it on a CPU. So I'm using the same model that I created in the previous step. That's a deep model. And then I am going to, most of the information is same. I'm just going to run it for 5 epoch, because on CPU you can see how slow it is. So if you see here, everything is CPU now. There is no GPU used at all. It's going to take less than a minute again, but it's going to be slower than what we saw with an GPU based implementation. So again, it's a little slow. The reason is like the model is not complex, but as we increase the model complexity, GPU and TPU helps in better vectorization, and because if you see we have multiple hundreds of neurons, you can vectorize it and run it efficiently on a GPU. A CPU has limited cores, so basically there will be a kind of latency when you take a matrix and execute it. It has to kind of buffer and then execute it, so it will take some time. but in our case we had just 32 convolution filter. Still CPU is slightly slower. Now what I'm going to do is I'm going to load the model that we created. We created a model and we finally saved it. So I'm just going to load the model. I'm just telling compile false so that my model is loaded false. My model is loaded faster. I don't want to wait for my model to load for this demo. So my model is loaded. Now what I'm going to do, I'm going to my test data set, and I'm taking 10 images. And then I am iterating over there, and then I'm basically calling the predict function of the model that I created, like basically the model that I loaded. If you see in the previous step, there is an fmints load. So basically what I'm doing is I'm just calling an predict function that will give me the probability outcome. And I'm just showing the image, what was the image, and I also have a label in my test data frame. So when I am iterating to the test data frame, you can see there's an image and label. I am printing the actual label and I am printing the predicted label. So what is predicted and what is actual and what is the image? So let's quickly see, like for 10 images, how much did it predict? We know the model is only 74% or 75% accurate because I'm setting the best model, right? So let's quickly go through and see. Let me go to the top and check it out. So you are seeing all this logging for each step because I have enabled that particular session. If you disable it, it will not be there. Now the first one is shirt, but it predicted a pullover. So there is an issue. The sandal, it predicted properly. It's a sandal. The actual label and predicted label are sandal. And then let's go to few others. The t-shirt, it predicted properly again. Similarly, trouser, it predicted properly. Again, the other trouser, it did not predict properly. Basically, it says it's a dress. So again, we know that our model is not, we can still tune the model. We can increase the complexity. The ankle boot, it predicted properly. So now we kind of know that, okay, how you can take a model and distribute it, what are the ways of distributing it, and then we just saw a complete walkthrough of TensorFlow to how to take the model and kind of use it for prediction. Now in the next video in TPU, I am going to stay out of any of the deep learning models. I am going to take simple functions and see how I can execute those functions on a TPU device. Thank you.